Let's learn about the RISC-V ISA family. Now, what an ISA is actually matters quite a lot in this class, and so I prefer this definition from the ARM glossary rather than the Wikipedia definition. An instruction set architecture, or ISA, is part of the abstract model of a computer that defines how the CPU is controlled by the software. So this has to do with the assembly language, and basically the assembly language is how the CPU is controlled by the software. Now, from the RISC documentation, it says a RISC-V ISA is defined as a base integer ISA, which must be present in any implementation, plus optional extensions to the base ISA. And it says, although it is convenient to speak of the RISC-V ISA, RISC-V is actually a family of related ISAs, of which there are currently 4 base ISAs. So that's my emphasis. RISC-V is actually a family of related ISAs. So let's learn about the ISA family. The ISA family. So here we go. We've got the RV64I, 64-bit integer, RV32I, 32-bit integer, RV128I, 128-bit integer, and RV32E, 32-bit embedded. So let's learn more about each of them. In the RV32-bit I integer ISA, you have 32-bit pointers, and all the registers and pointers are 32 bits wide, and there are 32 general-purpose registers and a single special-purpose program counter register that points at the next instruction to execute. And there are 40 instructions in this RV32-bit ISA. So these are the instructions we're going to be learning about throughout the class. They actually break up into different groups. So here we've got some loads, here we've got some stores, we've got some arithmetic, Boolean operations, and so forth. So we'll learn about all that throughout the rest of the class. In the RV32E for embedded ISA, you still have 32-bit registers and pointers, but the key thing is that they cut it down from having 32 general-purpose registers to having only 16. Now, at the time of writing and recording this class, this is not yet actually ratified, but it's generally understood that it'll behave basically the same as RISC-V 32-bit I, and then they just have less registers. Now, why is that? Well, they include their motivation in the documentation. It says, we have found that in small RV32I core designs, the upper 16 registers consume around 1/4 of the total area of the core, meaning the physical silicon die, and excluding memories. Thus, their removal saves around 25% core area with corresponding core power reduction. So basically, if you get rid of some registers, then you're going to save power and space for the actual silicon fabrication. And space is at a premium because the smaller the chip, the more of them you can get on a silicon wafer, and that means you have increased yields and increased profits. The RV64I is the 64-bit integer ISA, and here the registers and pointers are all 64 bits wide, and there are still only 32 general-purpose registers and the program counter. Now, RV64I is a superset of the RV32I. RV64I includes all of the instructions from RV32I, and then it adds 15 new instructions, which are mostly for when you're dealing with 32-bit operations, but you happen to have 64-bit registers. So in this class, the lab environment that we're using, the Docker container, actually is running QEMU that is only capable of executing RV64I binaries. And so although it can use RV32I instructions, the binaries themselves are compiled for 64-bit. It assumes 64-bit registers and so forth. So I may fix this. I may add 32-bit support at some point in the future, but when this class was first made, we only supported RV64I, and you should assume that you're always dealing with the base 40 from RV32I, these base 40 right here, plus the 15 that are added by RV64I. And you can see in the documentation it says RV64 base instruction set in addition to the RV32I. So here's our extra stuff. There's going to be a whole bunch of W suffixed things, which is going to be our hint that it's something that deals with 32-bit sizes, word sizes, instead of 64-bit sizes. And then finally, the last base ISA is the RV128-bit I, RV128I, and here you move up to having 128-bit wide registers and pointers, but you still retain only 32 general-purpose registers. Now, like RV32E embedded, this is not actually ratified at the time of writing. And they gave some motivation, justification, and essentially comes down to supercomputers and the recognition that sooner or later they're going to need more than 64 bits of space. They're guesstimating, perhaps by the 2030s. And so consequently, they just want to recognize that they're probably going to have to move up to 128 bits of space. And rather than doing, subsets like other architectures when they try to move past 32 to 64-bit, they put little slices, first you have 48-bit and then you have 52-bit. Well, they just say like, hey, look, let's just move up to 128-bit when we get there. Now, as the RISC-V document said a few slides ago, you can also have numerous extensions to the base ISAs. And indeed, most of these extensions are frequently used to create what they call the general purpose ISA. So they have RV32G and RV64G for the general purpose, and that means you include also you start with the base ISA for integer operations, and then you include extensions M, A, F, D, ZISCR, and ZFENCY, and we'll talk about those in a second. But the basic nice thing here about RISC-V is that theoretically, you could get away with a computer that only uses the base ISA, and then, you do emulations and libraries and whatever to achieve something like multiplication. So the key thing is that the silicon makers can only include those extensions that are actually required for their purposes. Now, if they're building a general purpose computer, then they're probably going to do this RV32G or 64G. So here's our ISA family extensions, and sorry to change decades on you here, but we've got our RV32i, 128i, 64i, and 32e that we just talked about. And then we have the M extension, A extension, F extension, D extension, ZISCR, and ZFENCY. It's the Adams family extension. ISA family extensions. The first extension is M for integer multiplication and division, and they separate the multiply and divide out from the base to simplify low-end implementations, basically something that doesn't actually need multiplication, or for applications where integer multiply and divide operations are either infrequent or better handled in attached accelerators. So they're big into the idea of accelerators in RISC-V, which is the notion that maybe you build, and it's a notion that goes along with current silicon practices, maybe you build an accelerator off to the side that's like dedicated silicon specifically for particular types of operations, such as, audio video processing, things like that, neural nets, and so forth. And so in those situations, maybe your base CPU doesn't have multiplication, but there's some other accelerator off to the side for other purposes, and you use that for multiplication. So this is covered in Chapter 7 of the documentation. Then we have A for atomic instructions. The standard atomic instruction extension named A contains instructions that atomically read, modify, write memory to support synchronization between multiple RISC-V hearts running in the same memory space. So first, atomic, if you're not familiar, it's this notion of an uninterruptible sequence. So you have situations in computers whenever you have parallelism where potentially, one thread of execution could modify some memory and then another thread of execution could read it like before or after the modification. That's where we have race conditions, and consequently the two threads would not see the same thing when you actually want them to see the same thing. So atomic operations say, let's make sure that this can't be interrupted so that when this operation completes, when the write is complete, then everyone sees the same thing. And that's where they're referencing hearts. So what is a heart? A heart is a hardware thread in RISC-V terminology. So the way they define it, a component is termed a core if it contains an independent instruction fetch unit, and a RISC-V compatible core might support multiple RISC-V compatible hardware threads, or hearts, through multi-threading. So you may be familiar with this in the context of Intel systems, for instance. There's this concept of simultaneous multi-threading, SMT, and on Intel systems you may have heard that each of your cores actually has two threads of execution to it. They call it hyper-threading, but it's basically this notion that an individual core could actually have like more registers. You could have enough registers and other state in order to make it so that to software and operating systems and things like that, the core looks like it was two cores. And so if it was doing threading from a software perspective, it's actually able to, context switch between two different environments that have completely different sets of registers. So Intel systems and hyperthreading is the most basic, where you have two threads, two hardware threads, and other architectures like IBM Power 9 can actually support up to 8 threads per core. But the key point of a heart or hardware thread is just it's something that to software looks indistinguishable from having sort of multiple cores. And so software can take advantage of this and context switch between the two. Then we have the ZISCR extension, which stands for Control and Status Register Instructions, CSRs. RISC-V defines a separate address space with 4096 control and status registers associated with each heart. So again, it's per heart. So if the device has multiple hearts per core, then it's going to have multiple of these control and status registers per core. And that's why I say it's not just like the general purpose registers. You have to have the full extra register state for each individual heart. So Chapter 9 defines the control and status register instructions, and it says while CSRs are primarily used in privileged architecture, which is not the context of this class, there are several uses in unprivileged code, including for counters and timers, and for floating point status. Counters and timers are no longer considered mandatory parts of the standard base ISAs, so the CSR instructions have been moved out to a separate chapter. So basically, ZISCR, at some point, they said like, okay, we'll have the control registers as part of the base ISA. And then eventually they said, nah, that's not required anymore because we don't need these counters and floating point status stuff. So let's move it out, have it be an optional thing. Now, it's optional. It doesn't have to be included. You could have something that completely doesn't use it at all. But if it's going to do things like floating point status and counters and timers, then it's probably going to include those because these are prerequisites for that. So ZISCR is very much the kind of thing that is more appropriate for some future Architecture 2005 class that's more analogous to our Architecture 2001. In 2001, we covered the privileged and, OS internals elements of x86 architecture, so 2005 would be the same thing for RISC-V. ZFENCI is another extension, and this extension includes the FENCI instruction that provides explicit synchronization between writes to instruction memory and instruction fetches on the same heart. Currently, this instruction is the only standard mechanism to ensure that stores visible to the heart will be visible to its instruction fetches. So the basic idea here is if you're going to be overwriting your own code and then fetching it and actually executing it, like you might do with just-in-time compilation or like some malware does with polymorphic malware, you have to use the FENCI instruction to say, hey, by the way, I just did a write. Now make sure everything's synchronized so that when I read it back to execute an instruction, that I actually see what was just written. Without the use of this FENCI instruction, you would read back from memory, but you would not see what was just actually written. Now, FENCI should not be confused with FENCE, which is part of the RV32 base ISA. So FENCE just has to do with general reading and writing and making sure that there's memory synchronization, whereas FENCI is specifically memory synchronization for fetching instructions. Then we've got the F extensions, which have to do with floating points. And so this is the single precision floating point that is compliant with these IEEE standards. And also you can't have this F extension unless you also have the ZISCR or ZCSR, because it depends on that. And then the D extension is just double precision. So F for single precision floating point, D for double precision floating point, again, conforming to some IEEE standard, but we're not really covering floating point in this class, so we're not actually going to care about this. And again, the D depends on F depends on ZISCR. So RV32G is going to be RV32I, plus ZISCR, ZFENCI, A for atomic, M for multiply, F for single precision floating point, and D for double precision floating point. That is RV32G, a base ISA plus some set of extensions. Now, what does our GCC use in our lab? If we run gcc --verbose and we look through all this gobbledygook, we eventually see this with Arch RV64GC. So what is RV64GC? Well, replace the RV32I with an RV32I plus RV64I, then get all the rest of that for G, but then the C implies that we have another extension, the C extension. What is the C extension? Well, that is compressed instructions. So a standard assembly instruction in RISC-V is encoded in 32 bits, but if you use the compressed instructions, then you will have 16 bits instead of 32 bits encoding the assembly instruction. So this is going to be commonly used when you're trying to get smaller code size. Now, you may be familiar with other architectures like ARM has a notion of thumb and MIPS has micro MIPS. These are other ISA's approaches to compressing their code so that you can take high frequency code and have it take up less space. CISC ISAs like x86 don't need to have a separate sort of compressed mode because they have variable length encoding. So an x86 assembly instruction could be 1 byte, 2 byte, 3 byte, 4 byte, 5 byte, 6 byte, all the way up to 15 bytes. So they can be really long or they can be really short, and as long as they are using some of these short instructions, then they'll get better code size. So chapter 16 to cover the compressed instructions. So in this class, although this is what the compiler is compiling for, RV64G-C, we're only going to cover the following. So we cover the RV32I and 64I, those 55 instructions, the M, multiplication and division and remainder, and the C for compressed instructions. And we're not going to cover every single compressed instruction under the sun. We'll just cover them as they come up in the context of alternatives being used for our 32 and 64-bit instructions.